We did. So guys, starting into this next unit and starting into these ideas of energy and energy types and energy transfer and kinetic and potential energy and work and heat and all of this stuff. Guys, what do you want to look at relative to this first homework assignment? Yeah, Kate, go ahead.
For the first problem, letter C.
Okay.
I understood basically everything, but then it specified at impact. I just don't understand how to...
Okay, let's take a look. So as I'm thinking about this, as you're asking the question, I'm realizing this is question 1, which tells me it's going to be a broad, generic question and maybe visual, because remember, those are all at the beginning of the end of the chapter. So do we need to do A and B in order to understand C, or do they stand on their own? I think they stand on their own. So it says, if a heavier book fell from the same shelf, would it have the same kinetic energy when it strikes the floor? So we do need to go back. So it says, how does the book's kinetic energy and potential energy change as it falls? And you, just like our block, right? That up here we have lots of potential and no kinetic, and as it falls it accelerates and potential becomes kinetic, right? Okay. And then letter B says, what is the total kinetic energy at the instance before it strikes the floor? And the idea is that the amount of energy that it has right before it hits the floor is whatever potential energy it had to start with, because at that moment all of potential's been converted to kinetic. Is that okay? Okay, and then it says, if a heavier book fell from the same shelf, would it have the same kinetic energy when it strikes the floor? And the answer is no, because kinetic energy is a function of mass and velocity, and the higher the mass... Hey,
Hi.
Where have you been?
I was sick.
Liar. Don't...
I'll talk to you later.
All right. I love that kid, but I may kill him. So the idea, and so there's several things we can talk about. One is, where does the kinetic energy come from? And this isn't something you need to be able to quantify, but the kinetic energy when the book hits the floor is converted potential energy. So the potential becomes kinetic, but potential energy is mgh. So it's the mass, the force of gravity, and the height. So a heavier book would have more potential energy at any given height. But then when that potential energy becomes kinetic energy is 1/2 mv squared. And there's our mass again. So a heavier book would have more energy when it hits the thing. Is that okay? Did that get to your question? Is that all right? Okay. What else, y'all? What else do you want to talk about? Yeah, Maddie. Okay, let's take a look. And Christian, here, let me do this before I forget, because I'm horrible at handing out notes once apparently you're going at 9:30. The screencast is recording unless I screw something up. So if you miss a gap, you can catch up on it there. Number 3. Okay, so there's a couple things I'd like to talk about with number 3, whether this is your question or not. But let's look at this. It says, consider the accompanying diagram. And I want to talk with you about that in a moment. It says, does this diagram represent an increase or a decrease in energy? Okay, so let's just get into this. So, guys, this is something that you've never seen before, but this is something that you've got to learn to make sense of and draw a lot. So, guys, let's take a look at this diagram in number 3. So this is what is called an energy diagram. And it is the most generic graph that you've ever seen. But here's what you need to know. Hey, buddy, just set it down. So over here on the y-axis, you've got internal energy, and this is small, and this is big. So typically you won't even see units on these diagrams, but what you will see is it's always internal energy on the y-axis, and it's small at the bottom and it's big at top. Then, guys, there are no units on the x-axis. It's more of a picture than it is a graph. But then you'll notice that they give us this. They give us a line down here that they label reactants, and then they have a line up here that they label products. So as reactions take place, we know that reactions always go from reactant to product. So with that in mind, let's answer the questions. So letter A says, does this diagram represent an increase or decrease in the internal energy of the system? And Maddie, the answer is increase. The reactions always go from reactant to product. And when you read, and guys, this is to all of you, obviously, when you read these diagrams, read them with the idea that elevation is analogous with energy. So the higher something is, the more energy it has. So if we go from reactants up to products, energy is going in, so this would be an increase in energy. Yep, it would actually look like this. That's reactants, and this is products. And we're going to draw these so just get used to it. We're going to draw thousands of these. Yeah. So was that the heart of your question? You said you were exactly backwards.
I was exactly backwards.
Okay.
What I was thinking was that the energy was going from the reactants to the products.
Oh, yeah.
Because it was releasing the energy from the product. I couldn't understand.
Yeah, right.
Because I'm
Yeah.
Of course, it's not going to have the arrow pointing to the reactant.
Right.
But
Right.
Now I understand it's just. Yeah.
Is that okay? But here's a really interesting thought. And guys, this right now may be beyond your ability to understand, but it won't be in a couple days, but we can say it now. So Maddie, you said this, that energy is going from the reactants to the products. And now you understand that that's not correct, but we can also say that it's impossible. So and let's connect this because we need to understand this. So if a reaction is going to gain energy, it has to come from the surroundings, right? Because if our system is the reaction, we know that kinetic and potential can interconvert, but the total can't go up or down without an interaction with the surroundings. And that's what's happening here, is energy is coming in from the surroundings, causing the reaction to have more energy as products. Yeah, it's interesting. What else, y'all? Are we done was that 3? Are we good on 3? Guys, anything else you want to look at relative to the homework questions? You guys really okay? Okay, so guys, let's do this. Tuck those away. We're going to record performances there. Then guys, you are going to need note-taking materials and a calculator. And we're going to dig in. Wow. The scary part is even when you tell me to pause it, I still screw this up. Okay, big deep breath, focus. Okay, so guys, back to this idea of this being midterms. For those of you that are keeping an eye on your grade, which I think many of you do, you may have noticed a couple things. One is that with the summer quiz and the summer homework, those assignments are scaled. It was 65 points on the summer quiz, but I can put in a scaling factor that either magnifies or reduces the impact of those 65 points on your grade. And so frankly, I don't remember what scaling factor I put in there, but functionally what it does is it kind of makes the assignment worth less points. So instead of 65 points, it's actually worth 19 and a half. So what I do is let me look at what the scaling factor is. So the scaling factor is 0.3. So guys, this assignment is actually counting for a third of the 65 points. That explains when I type in your score, it divides your score by 3 and not just the total points by 3. Anyway, long story, but here's the deal, guys. For those of you that didn't yet pass that summer quiz with a 90%, that assignment is currently excused in your grade, so it doesn't bring your grade down. That's going to change this week. I'm going to pull off the check marks that tell Skyward to not count that in your grade, and your zeros are going to stick. Not stick, but your zeros will count towards your grade. Guys, understand that when the quarter ends, you're done. So you're welcome, as you knew, to come and start working on taking this thing again. The other day I told 3 of you that you all passed it. You have to get 90%. And then understand at the end of the quarter, we're just done, y'all. You got to get on this. So I will pull off those check marks so that it does start to impact your grade. With that said, Wednesday's a short day, right? On Wednesday, guys, I'm going to give your tests back to you, and we are going to spend time on Wednesday rewriting these tests. Normally, we won't do that. Normally, we don't spend class time rewriting tests, but this first one I like to do together just to develop some good practices. So on Wednesday, we're going to work on rewriting the test. And we'll talk more about that later. So, guys, do you have any questions about calendar or class stuff, or you guys are okay? Okay, so let's dig in. Let me do this and this and this. Isaac, were you doing something school related?
Yeah.
Okay. I just needed to change your attendance really quick. All right, so that's gone and that's gone. We love you. We'll miss you. Everybody say goodbye to Christian. And that's gone. That's not funny. All right. All right, so guys, you have to make me a promise before we get into today. And the promise is this. No matter how badly you want to, do not go out and Google first law of thermodynamics. Because when you do, where's it going to take you? Wikipedia. And you're going to start reading the Wikipedia description of the first law of thermodynamics, the first law of thermochemistry. They're the same. And it is going to stink and blow your mind. So, guys, understand, just like that. So, guys, understand that as we get into the first law of thermochemistry or dynamics, same thing, what we are doing is we are narrowing an amazingly large and complicated idea down to the fundamentals that we need to understand in order to functionally use this for the rest of the year. It is the very small tip of a very large iceberg. So guys, understand as you do get deeper into this, when you get into physical chemistry, if you pursue chemistry as a degree, there's a lot more to this. What we're doing is distilling it down to the essentials so that we can talk about this in a clear and concise way. So, guys, with this said, let me explain to you what we're going to do today. We're going to start by reviewing. We're going to go back over everything that we talked about with the block last time. We're going to go back over all of that on one slide. My students typically find this worth writing down because it's a very concise summary of everything that we did last time. Then, guys, what we're going to do is we're going to take these ideas that we already understand and we're going to begin to talk more about how chemical reactions exchange energy. And then, guys, at that point, we're going to get to this idea of enthalpy. Do you remember when you got to enthalpy when you were doing your chapter summaries? And do you remember thinking to yourself, what the snap? I don't understand what that means. That's my job. So guys, understand that when I teach you, when we talk about, when we explore this idea of enthalpy, your response is going to be, really? That was it? And guys, the answer is yeah, really, that's it. It is not a terribly overwhelming concept. I think as we ease into this together, you're going to go, okay, I understand. Again, guys, enthalpy is another one of those things you want to be careful about Googling, because if you get on Wikipedia, you're going to see it's a much bigger idea. But as we bring it together to this thing that we need to be able to think and talk about, you're going to see that it's not as complex as maybe you thought. So guys, first of all, review. Ready? This is everything that you should be able to say amen to. Understanding that amen is not a church term. It just means we concur or agree. I've never used the word concur in my life, so I concur. I'm going to try, though. I'm going to see if I can sneak that in somewhere. Why, yes, Josh, I concur. It'll be lovely. All right. So guys, it goes like this. When we think about the exchange of energy, the first thing we have to identify is a system. If you want to try to draw this with me, I would skip down like 3 or 4 lines, and I would draw a box about 2 inches square. Let's use metrics, 5 centimeters square. And I concur. And I was going to say amen, but... And guys, as we do this, one of the most important things we've talked about is this concept of system. This is one of the beautiful things about having the lab opportunity that we do in this class, is you can easily draw a box on a paper and go system. Wait until you get into lab and you have to start figuring out what your system is. It's a whole different game. And so guys, as a result, we're going to get really good at system. But the thing you need to understand right now is there's power in being able to identify your system. And guys, you're going to become very strategic at saying this and only this is my system. Because it radically changes the math as we start chasing energy. So guys, once we identify our system, what then does everything else become? The surroundings. Oh yeah. Oh, snappy. So guys, once we have system and once we have surroundings, we need to remember that when we talk about energy and energy transfer, we are not oversimplifying this picture because this is only AP chemistry. And you guys understand that, right? That this is freshman college chemistry. It feels like the end of the world, but wait until your junior year in college when you look back and long for general chemistry, your freshman year. So guys, this is not dumbing this down. They're not going to get you your sophomore year and go, hey, yo, guess what? There's more to this picture. This is it. Guys, within your system, there's 2 kinds of energy. Those are kinetic and potential. Cade got us thinking about this with question number 1 in the homework. Guys, kinetic and potential energy, like the falling book or the falling block, these things can interconvert. They are both what we call forms of internal energy. As a matter of fact, internal energy is the sum of those 2. And kinetic can become potential and vice versa. And guys, when that happens, what happens to the internal energy of the system? Let's say that again. When kinetic and potential energy interconvert, what happens to the total internal energy of the system? It stays the same, right? You good on that? Okay, so guys, if converting between kinetic and potential doesn't change the internal energy of the system, how do we change the internal energy of the system? It's got to be an interaction, yes. It's got to be an interaction with the surroundings. But guys, the surroundings only have 2 ways of influencing the system. And what are they? Work and heat. And guys, that's it. We got work, we got heat, and that's it. And again, guys, this is not dumbing this down. This is it. We live in this amazingly intricate and yet fundamentally amazingly simple universe. Sometimes I think those are... I wish just once we could take this group of people and go over to seminary and really talk about this. Like, holy smokes. It's pretty cool stuff. So, but we can't do that. Actually, we probably could do that here, but I'd still go to jail, so we won't. All right, so guys, this is it. This is the whole picture. We've got our system, we've got our surroundings. The system has internal energy, which is the sum of the kinetic and the potential. Those can interchange with no net change in energy. Energy of the system does change by interacting with the surroundings. That only happens through work and heat. What do y'all need to talk about? You guys settled on all of this? Okay, so in summary then, guys, I don't think you need to write this down. You should be able to say, Josh, I concur. Can we just do that? So, energy within a system can convert from kinetic potential to kinetic and vice versa without changing internal energy? Energy can transfer between a system and its surroundings in the form of work and heat. I concur. Could you guys try to work that into your AP test? That would be awesome. Extra points. All right. Guys, are you really okay? This all makes sense. Okay. So guys, with that said, here's the hazard of today. As we get deeper and deeper into what we're going to do today, some of you are going to start to go, wait a minute, haven't we already talked about this? Didn't we do this last time? Isn't this still review? And the answer is yeah, kind of. Because what we're going to do is we're going to come back to these interesting ideas that we all can concur about. Is it about or on? Do you concur about? Doesn't matter. So, guys, we're going to come back to these ideas that we all own and understand, and we're going to come back and re-muck with them as we move towards this idea of enthalpy. So it is going to start to feel like review, and you're going to be like, wait, am I missing something? Because I thought we already talked about this, and we did, but we're going to reorganize these ideas because we're on a journey towards enthalpy. So guys, as we do, we need to first of all lay out the governing principle that's going to guide this entire conversation, and it's the first law of thermodynamics. And we all agreed that we're not going to look this up. And guys, when you do look this up, because let's be honest, you're going to, this is not the definition that you are going to see on Wikipedia. But it's hidden inside all the big words that most of us don't understand, including me. Here's the distillation. The first law of thermodynamics says this: energy is neither created nor destroyed when changing forms or transferring between a system and its surroundings. And I really would love to give you the opportunity to write this down word for word. Energy is neither created nor destroyed when changing forms or transferring between a system and its surroundings. Now guys, as you're writing down these words, if you are not reflecting back in significant ways to the diagram that's at the top of your notes, you're missing the point. So why don't we make these connections? Guys, could you take these two words right here, changing forms, and could you draw an arrow back to where that's represented in your diagram above? And then guys, could you circle then the word transferring? And could you please then draw an arrow or arrows, nudge, nudge, wink, wink, back up to your diagram to show where that's represented in the diagram that you drew above? So guys, let's talk. Where in your diagram, and I'm just going to sketch it really quick. So this is the system and energy kinetic, energy potential, work, and heat. And clearly that's a horrible drawing, but it will suffice. Guys, where did your changing forms arrow go? Yeah. Guys, this arrow goes right here. This is what we're talking about. The forms of energy within a system are kinetic and potential, and we've already established that those can interconvert with no net change in energy. But then, guys, when we talk about transferring, where did those lines go? Where did those arrows go? To heat and work. And guys, to those arrows are talking about things that we've already discussed. The only way for energy to get in and out of a system is work and heat. You guys settled with this? So given the rest of the sentence, what do you now understand about the things that you understood what's your new understanding about these ideas of interconversion and work and heat? Exactly. Guys, when these things happen, when kinetic and potential energy interconvert, and when work and heat provide conduits for energy transfer between the system and the surroundings, energy is never created or destroyed. And now you're going, wait a minute, I've heard this idea of neither created nor destroyed In what other context? Law of conservation of mass. So guys, there's this idea that matter is never created or destroyed. Now we have an additional idea that importantly says that energy is never created or destroyed. And it's such a related concept that we actually call this the law of conservation of energy. In the same way that matter is conserved, energy is conserved. Whether it's an interconversion between kinetic and potential, or whether it is a transfer through work or heat, guys, energy is conserved. Which brings up an amazing question. If energy is conserved, and if matter is conserved, where did it all come from in the first place? And guys, I would propose to you that that's a question that science can't answer because it's immeasurable. There's no way to take a measurement that tells us where energy and matter came from. With that said, we can talk about this. We now know that energy is conserved. We also know that matter is conserved. But do you know that they can interchange as well? Says who? It's always Einstein, right? You guys notice that? That all great quotes, whether he said it or not, come back to Einstein? Well, guys, this one, Einstein actually did say. So we understand that energy is conserved. We understand that matter is conserved. But guess what? Energy can turn into matter, and matter can turn into energy. They are interchangeable. In the mind of an advanced physicist, matter is just condensed energy. That's a big thought. Yeah. No, so this is E. And guys, understand this is not an equation that you need to know. It's nothing we're ever going to solve, and it's also not something that's part of the curriculum. But we can talk. We know that energy is conserved. We know that matter is conserved, but those two things interconvert. So this is energy, this is matter, and they can interconvert. Matter can turn into energy, energy can turn into matter. Guys, when we blew up that bomb over Hiroshima, leveled the entire city, we're not exactly sure of the mass, but somewhere between 2 and 10 grams of plutonium or uranium, depending on if it was Hiroshima or Nagasaki, somewhere between 2 and 10 grams of whatever that material was got converted to energy. And that was the energy that destroyed those cities. So guys, understand that when matter does turn into energy, it's an amazing process that's quantified by squaring the speed of light. So again, the entire town of Hiroshima was leveled by about 2 grams of matter turning into energy. So the math is unbelievable. But guys, literally, when that bomb went off, the world became 2 grams lighter. Because 2 grams of matter was not conserved. 2 grams of matter was converted into energy. So when we say that matter is conserved, that's in chemical processes. In nuclear processes, matter and energy interconvert all the time. And it went the other way in the Big Bang. In the Big Bang, that thing that exploded was just a bundle of energy, and as it expanded, it cooled and turned into matter. Literally, energy condensed and turned into matter. So it's interesting. We're not going to dwell on it. Go ahead, Isaac. Sure, but understand you just are talking about something I don't understand. So I'm going to say yes, and then we're going to go on. Yeah. So, but no, in all honesty, so the Higgs field is actually the field that they're understanding now causes things to have mass. And so, yeah, and it's interesting. We are going to start talking about these everywhere permeating energy fields when we talk about electrons, because there's an electron field as well. Yeah, go ahead. Speed of light. So this is 3 times 10 to the 8th, and then square that. So take that number, square it, multiply by the mass, and that's how much energy you get out when matter turns into energy. Yeah. So, guys, fundamentally, this is where we need to be. We need to understand that mass is conserved, but we know that since last year. Now we understand that energy is conserved. And guys, when we say energy is conserved, it comes back to this. Kinetic becoming potential, or through work or heat, energy is not gained or lost. It's just interconverting or moving between the system and the surroundings. Is that okay? You got to understand that fundamentally. Things you want to talk about? You guys good? Okay. So guys, with that said then, we need to start digging into these ideas so that we can then change them a little bit so that we can finally understand enthalpy. So to do this, guys, we need to come back to internal energy. You already know something about internal energy. What makes up the internal energy of a system? Kinetic and potential. So guys, we understand this, and this is new. You're going to want to write these down. So guys, when we're studying the total internal energy of a system, we have got to study all of the sources of energy within that system. And we call this internal energy, and it's abbreviated E. Now guys, the internal energy of a system, as you already know, is the sum of all of the kinetic and potential energy in the system. And you're going, I told you, this is going to start feeling like review again, right? Because it is. Guys, this is review. We've already talked about this. But this is going somewhere new. So we understand that this idea of internal energy, something that we abbreviate with an E, is the sum of the potential and the kinetic energies. Or we could say it this way mathematically. E is equal to E sub k plus E sub p. Kinetic plus potential energy. Again, guys, review, right? But because it's review, don't tune this out because we're about to say something really important. You guys with me to there? Okay. So guys, do you remember when you got to the portion of chapter 5 where it talked about state functions? Do you remember that? Okay. So guys, if you took the time to read carefully through this idea of state functions, hold on to that word, those words for a minute. And now let's talk about this. So guys, we're in agreement that internal energy is kinetic and potential. But now we need to make this more meaningful and more realistic. And we need to talk about how do we measure the internal energy of a system? How do we do this in lab? If we want to go into lab, because everything that we learn in here has got to be reproducible in lab. Guys, how do we go into lab and how do we measure internal energy? And the answer is we don't. Guys, this you've got to write down. Internal energy cannot be measured. You guys understand the word empirical means measurable? Did you know that or no? Yeah, guys, the word empirical means measurable. So an empirical formula is a formula that we measure in lab. Guys, internal energy cannot be measured. There's no such thing as an internal energy meter. We can't directly measure internal energy. Let's talk really briefly about why not. Guys, fundamentally, what is energy? What was our definition? Okay, so it's the ability to do work or exchange heat. But we add an even more generic definition of energy, which was what? The ability to make a change. How do we change things? Work or heat. So guys, which other definition you're clinging to, here's the idea. Energy is fundamentally the ability to change things. And if you have a system, the only way to measure its energy is by allowing it to change things and then measuring how it affects other things. So guys, the idea is this. Fundamentally, we can't directly measure energy. Instead, what we measure are energy changes. Let's say that again. We cannot directly measure energy. And by we, I don't mean you and me, I mean anybody. You can't directly measure energy. What you can measure, because energy is the ability to make a change, you can measure how energy changes with the system and its surroundings. But guys, you can't directly measure it. Do you buy that? Is that just a second? Do you buy the idea? This then comes back to state functions. So guys, here's the deal. State functions explain why this is the case. But guys, my experience over the years that I've taught this class is trying to help you understand state functions is not a good investment of our time. You might see a multiple choice question or two on the AP test over state functions, and you're either going to get them wrong or you're going to guess. But guys, understand that state functions are a really big deal. And when you get typically to your freshman physics classes, a little bit in chemistry, mostly in physics, you're going to have professors that are going to talk a lot about state functions. Your dad is going to hate what I'm saying right now. Right? Don't tell him I said we're not going to do state function. He actually already knows. So, guys, understand that state functions are a big deal. But it's a concept that we don't have to grasp in order to go where we're going to go with this. So here's the deal. Energy cannot be directly measured. Why? Because energy is the ability to make a change. So in order for us to measure energy, we have to measure change. This comes back to the idea of state functions, but we're not going to dig into it. So Isaac, I'm going to ask you to carefully consider the question that you're going to ask, understanding that you're a part of a bigger group and you need to move all of us in a positive direction. But understand that that thought needs to apply to all the conversations we have, because you know that the Higgs boson field has nothing to do with this class. So be gentle. Okay, go ahead.
Couldn't you, if you had no energy and then you added it, you couldn't measure how much energy you might add?
But that's the point, is it's the adding that we can measure. We can't directly take an object and say that has no energy. But we can add energy to it and see where, but it's the changing that we're measuring and not the energy directly. And I know that seems sort of like we're splitting hairs. When we get into lab, it'll make more sense. Yeah?
If we can measure mass, why we can't measure energy if mass can be converted to energy?
It's a great question. And so we can directly measure mass. We can't directly measure energy, but understand they're not fundamentally in our world the same thing. They come from a common origin, and again, I have to be careful, but they're fundamentally not the same things. But you're right. We can directly measure mass. We can't directly measure energy. Yeah, although it's interesting, Santiago, I'd never thought of it. Even when we measure mass, we measure by comparison. Right? How do I know that this thing weighs 5 grams? Well, the answer is because we've all agreed on what 5 grams is, and then we compare this to it. So even in that, it's still a function of comparison. Yeah, it's weird. You guys okay on this idea? Okay, so now we're going to talk, guys, no longer about energy, but about energy change. So as we discuss energy change, we can then leverage this idea, which, Maddie, is going to come back to your question from homework. So delta E, you guys all know that delta means change. So delta E, change in energy, is final minus initial. And so, if final, I'm drawing dots. And so, why will it not switch? You can do this? There we go. So if final is greater than initial, then that means that delta E is positive. And if initial is greater than final, that means that delta E is negative. You okay with that? Yeah.
Is this thing that potential energy really with energy at all?
I wouldn't have come to that. Help me understand what you're thinking.
Well, energy has to be change. If the potential energy is not changing.
So, but remember that energy is the ability to make a change. And if we take something as simple as like my pen and we put it here and we say that this is ground, then yeah, that pen has no ability to change anything because it has no potential energy. But when we lift it up here, it now has the ability to change something. I mean, I could drop it on Olivia's head and it would leave a mark. We changed her head, right? And so the idea is that it very much is something. It's energy that is stored that then has the potential to change something. So, but understand that it's not energy doing anything. It's energy that could be doing something. Does that sit? Guys, are we okay on these ideas? Then let's do this. Draw a couple pictures with me. These guys. No, those are not beakers. I know that you're confused. Beakers have another side and they tend to be black. This, on the other hand, is an energy diagram. Now let's look. What would this look like in terms of an energy diagram? Well, final is greater than initial. So our energy final is up here and our energy initial is down here. And going from initial to final, if final has more energy, that means in the end we have more energy than we did in the beginning, and that makes delta E positive. Do you buy that? So then why don't you in the right-hand diagram draw the bottom one? Straightforward, right? So on this one, final is now down here, and initial is now on top. So the final is smaller than the initial. So we started at a higher energy, we ended up at a lower energy, and now this is a loss in energy, so delta E is negative. Is that okay? Yeah. No, and to be, yeah, great question. So it's been a long, long time since they've had us draw these on AP tests. But when you do draw these, typically when you're drawing graphs on an AP test, they will give you the grid and they will label the axes. With that said, what they're doing now more on the AP test is giving them to you and having you interpret them. But you're going to see this is like training wheels compared to, we're going to be looking at energy diagrams that have like 7 and 10 and 12 different tiers to them. But yeah, typically they'll label them for you. Yeah. So guys, you good on these ideas and the representations? So let me ask you a question. How does this happen? Whether it's a positive change or a negative change, how do those two things happen in the real world? Work and heat. Guys, grab that. How does this happen? How does energy get in and out? How does final energy end up higher or lower than initial energy? And guys, I know that we've talked about it, but you've got to bring these ideas back. The way that this happens is work and heat, right? So let's take that idea and go back up to the top of your page. And guys, let's now bring this back together like so. You don't need to worry about the words up top. As a matter of fact, I just want to get rid of them because they're probably distracting because we've said this enough already. So guys, it goes like this. We know that we've got our system and we know that we've got our surroundings, and you've already got this drawn into your notes. Now guys, we've also said that the only way to get energy in and out of a system is work and heat. But now notice how these work and heat arrows are different than the ones you drew before. How are they different? They have direction. The one that you drew previously was double-headed, right? Guys, please cross that double-headed arrow in your diagram out and replace them with this one. Now, guys, we've got to talk about this important idea, and then we can start to play with these. So on the previous slide, we talked about this idea of positive and negative change. Up until now, all that we've said is work and heat is how energy gets in and out. But now we're saying positive energy change and negative energy change. But guys, in order for that idea of positive and negative to make sense, we need a frame of reference. And guys, this is our frame of reference. You are always in the system. So on the previous slide, when we said positive energy change, that was for the system. What happened to the surroundings in that case? Guys, don't miss this. If the energy change for the system was positive, where did the energy come from? The surroundings. And guys, if we could quantify this, let's say the system gained 100 joules of energy. How much energy did the surroundings lose? 100 joules of energy. Says who? The first law of thermodynamics. Are you starting to fit the pieces together? So guys, the idea is this. If this is a positive change, meaning that energy went in, the surroundings experience an offsetting negative change of exactly the same magnitude. That's the first law of thermodynamics. Any energy gained by the system is lost by surroundings and vice versa. So with that idea, guys, now we can fully flesh out this diagram. So label these work, label these heat. I'm going to zoom in so you can see this better. So guys, let's do this. Remember, you are in the system. So if the system is doing work on the surroundings, is that an increase or a decrease in energy? You're hesitating. Let's do this. We are in the system. Our frame of reference is always in the system. So if I'm in the system and if I'm doing work on the surroundings, am I gaining or losing energy? I'm losing energy, that's negative. Now guys, what if the surroundings are doing, actually hold on, no. I don't know where this is going next. My next animation is gone. We're going to fake it. Well, let's see what happens. There it is. I don't know why that's not on there. So guys, what if the surroundings are doing work on the system? Then that's an energy increase for the system. So guys, what about this? What if the surroundings are adding heat to the system? Is that energy up or energy down? Energy up. Again, because we are in the system. And then guys, if the system is heating up the surroundings, that is a net energy loss. What questions do you have about that? The only new thing that we've done is we've lent direction and therefore signs to these changes. And again, guys, if you've taken physics, this is completely backwards. In the mind of a physicist, the observer is in the surroundings. In the mind of a chemist, the observer is in the system. So our frame of reference is always internal inside the system. You guys okay? Okay. Guys, here we go. It's now time to bring all these ideas together and finally talk about enthalpy. So guys, you understand from having looked at chapter 5 already that enthalpy is a big, big idea. But in order to get you to this idea of enthalpy, Going back to our previous diagram, we now understand as deeply as we need to that energy can come into a system, energy can go out of a system. Energy comes in by having work being done on the system or heat added to the system. Energy comes out of the system by the system doing work or the system losing heat. Yes? Now we're ready finally to talk about enthalpy. So guys, setting the stage, it goes like this. These are things you want to write down. So guys, when we talk about enthalpy, enthalpy requires that we assume that our chemical reactions take place in what we call open containers. Now guys, open containers, the term open container, you can use on the AP test. It is an accepted way to describe this. With that said, understand that they're actually what are called constant pressure containers. But you can call them open containers, and that's just fine. So guys, then the question becomes this. What is an open container? Guys, an open container is a hypothetical container which offers no resistance to expansion or contraction. What? Guess what we're about to do? Draw a beaker. You guys ready to draw a beaker? Can we draw a beaker? Let's draw a beaker. Well, let's do this. Let's draw an Erlenmeyer flask. Oh, I know. We're mixing it up today. So guys, we're going to draw ourselves an Erlenmeyer flask. And inside this Erlenmeyer flask, trying to think of a reaction that we could use that you would understand. So guys, let's do this. Let's keep it simple. No offense. Let's keep it simple. And let's just go, and I'll write it down below. You could write it in there if you want. Everybody's favorite redox reaction. Zinc and hydrochloric acid. So guys, as this reaction carries out, our products, and I'm not going to balance it, are zinc chloride and hydrogen gas. Yeah. And then we collected the hydrogen and lit it on fire and we giggled and it was all lovely. Yep. But guys, it's actually, as Maddie pointed out, good to remember this. So what do you see when you put zinc and hydrochloric acid? Bubbles. Did any of you happen to pick up the test tube when the zinc was reacting with the hydrochloric? Did any of you touch it? It's hot. Yeah. Guys, this reaction is very, very exothermic. It gives off a lot of heat. So if it's helpful for... Here, let's just do this the way this is. That's code for exothermic. You may as well just write it down with me. We're going to talk about it in a minute. Guys, that's code for exothermic. Delta H, change in energy, change in heat, and it's negative. That means energy is being given off. It's an energy loss. Guys, can you think about that for just a second? It's an energy loss. Because where are we in the system or the surroundings? We are in the surroundings. And so, guys, sadly, what that means is you are bobbing around in the Erlenmeyer flask of acid. That's where you are. So guys, this is our system. And understand that as we do this throughout the year, 98% of the time, our system is going to be the reactant and product species. Zinc, hydrochloric acid, zinc chloride, and hydrogen. That's our system. But guys, that's giving away energy. That is a negative energy change. How do we know that that's a negative energy change? Because we touched it and it's hot. See guys, the idea is this. Energy is coming out of this. Heat is going out. You're going to want to write these things into your notes. So guys, heat is going out. So the reaction is losing energy. Heat is going out. But guys, you ready for this? You already know that that is not the only way for a reaction to lose energy. Guys, what is the other way any system can lose energy? Work. You ready for this? Put a balloon on your Erlenmeyer flask. Now guys, we haven't done this in review yet, so we should. Actually, we're going to do this. I'm going to put, oh yeah. See, I have the advantage of being able to digitally erase. We're going to put an uninflated balloon. It'll get there. Guys, we're going to put an uninflated balloon on our Erlenmeyer flask. Now, we understand that there's another way that energy can get in and out of this reaction, and that is heat. Well, heat's there. The other is work. So guys, remind yourselves, what two things have to be present for work to be done? Work is equal to force times distance. So guys, in order for work to be done, something has to move, and there has to be an opposing force. So now guys, let's talk. This reaction can also do work. How? Say it again, Chase. What will happen to the balloon? It will inflate. And guys, that is typically the way chemical reactions do work. They do work through expansion. So this reaction takes place. We know that it loses heat, it loses energy in the form of heat because it feels hot. But then guys, these hydrogen molecules go up into the balloon and they make the balloon inflate. So guys, let's make sure that inflating that balloon meets the criteria for work. Is there movement over distance? Is there an opposing force? What is the opposing force? The elasticity of the balloon. So the balloon, left to its own devices, will not just magically inflate. That gas has to push in order to get the balloon to inflate. So this reaction can do work by inflating the balloon, moving it a distance against the elasticity force, and it does work. Do you understand how reactions do work? Now guys, don't miss this. This is the big idea. We are now going to replace... Oh shoot, I can't go back far enough. Guys, we are now going to replace this balloon with a magic balloon. And guys, let me introduce you to this magic balloon. This magic balloon is actually what is called an open container. And this magic balloon has the ability to expand and contract with no elastic resistance. It just magically knows how big or small it needs to be in order to house that gas. So as more gas goes in, it just magically gets bigger. And as gas comes out, it just magically gets smaller. And it doesn't offer resistance. Guys, this is what an open container is. An open container is a hypothetical container which offers no resistance to expansion or contraction. Does that now make sense? Do you understand what an open container is? Yes? If you don't, please ask. Do you understand what an open container is? Because guys, you're about to have a big old aha moment. You understand what an open container is, yeah? Okay, now guys, do this. In review, what can we do to change the total internal energy of a system? We can exchange heat, which is Q, or we can do work, yes? Yeah? So in the real world, when this reaction does its thing, we know that heat, Q, is coming out because it got hot. Then guys, we also know that work was being done because in the real world, the balloon resists expansion. And so in order for that balloon to get bigger, work has got to be done, right? But now guys, watch this. When we replace the real balloon with the magic balloon that doesn't offer any resistance, guess what happens? Work can no longer be done. Let's say that again. When we replace the real balloon with the magic open container balloon, work can no longer be done. Why can work no longer be done? There's no resistance. You good on that? So guys, this is what then changes. We know that in the real world, the way to get energy in and out of a system is heat or work. But if we carry out our reactions in open containers where work can't be done because there's no resistance, then this goes away. And if that goes away, what's the only other way we can get energy in and out of a system? Heat. But now we change the name and we call it enthalpy. Guys, that's all enthalpy is. Enthalpy is the exchange of heat in an environment where you can't do work. Again, enthalpy is exchange of heat in an environment where you can't do work. Yeah.
So that was hypothetical.
Yeah.
Is enthalpy possible in real life?
That's a great question. Can you hold that for a second? Because people are drawing and writing, and I want to answer that. So guys, Chase is going to already did ask the critically important question, which is basically, really? Does this really happen? And we're going to talk. So guys, let's make sure we're all clear on this. What is enthalpy? Enthalpy is the same as heat in an environment where you can't do work. You guys sold on that? So let's answer Chase's question. Is this like make-believe? Or is this really possible? And guys, the answer is, it's really possible. Because imagine this. Imagine if we actually did have an Erlenmeyer flask, and if we put some acid in the bottom of this, and then dropped in the zinc. What's this going to do? It's going to bubble. Where are the bubbles going to go if we don't put a balloon on top? Into the room. Do you now understand why we call these open containers? Because that's literally what we're doing. If we do the reaction in an open container, the hydrogen, which would have inflated the balloon and done work, can just go out into the room. And the room functions as our magic balloon that can just accept gas, because the room is so big that we're going to bleed gas out into the room, but the room is so big that functionally the pressure doesn't change. So, in theory, as hydrogen gas comes out of this flask, in theory, we are increasing the pressure in the room because we're adding more gas. But practically, we're not, because the room is so big that the pressure really does stay constant, and therefore we can't do work. That's why we call them open containers. Does that make sense, you guys? Santiago.
I know that sounds weird, but is there a way to make it opposite? Like in a word that only can change the word.
Oh, can you do work without the exchange of heat? Absolutely. Yeah, definitely. That's more a function of the reaction. So we're going to talk more in the coming days about where this heat comes from, and we're going to talk about that. But yeah, you can have reactions that tend to lose more energy through the form of work than heat. It's never perfect, but absolutely. So guys, other things you want to explore relative to this? You're okay? All right, so let's then put a fine point on this. And guys, it goes like this. What then is enthalpy? Enthalpy is heat that is exchanged in the absence of work, or heat that is exchanged under constant pressure. Now guys, you're not going to like this, but it's not my fault. You ready? Enthalpy is abbreviated capital H. How is heat abbreviated? Q. So heat is abbreviated Q. Enthalpy is abbreviated capital H. Seems like heat should be capital H, but it's not. So heat is Q and enthalpy is capital H. So now guys, similar to what we said before, we can now say this. Delta H, change in enthalpy, not change in heat, change in enthalpy. Although guys, I'll tell you right now, as we get more and more into this, especially in lab, we will call this delta H, we'll call it change in heat. Technically, it's really change in enthalpy, but because we do our reactions in open containers, we use them interchangeably. Is final minus initial. So if delta H is positive, that's endothermic. And if delta H is negative, that's exothermic. You guys doing good? So let's wrap up the day. So guys, we've now got finally this equation that we can think about that says the change in enthalpy of a reaction is equal to the enthalpy of the products minus, or I'm sorry, the final enthalpy minus the initial enthalpy. I kind of gave away where this is headed. So guys, if we apply this equation to chemical reactions, where do reactions finally end up? Products. Where do they start? Reactants. And that then brings us to this. It's the same equation, only it's applied to reactions where we've got products and reactants. And guys, this then leads us to what are called thermochemical equations. Yeah.
So when you're updating it, do you just take the temperature minus the other temperature?
No, because temperature and heat are not the same thing. Temperature is a measure of kinetic energy. Heat, or enthalpy, is a measure of this exchange of energy. But you ready? Okay, so you ready for, check this out, right? Yeah, you're like, do we just measure temperature? And guys, this is a common mistake. By the end of the labs that we're going to do over this, you won't make the mistake because you'll have enough hands-on experience. But temperature and heat are not the same thing. Temperature is a measure of kinetic energy. Heat is an exchange of energy. No, finish writing because I know you're jotting down ideas, but I want you to finish because I want you to make... Are you okay? So here's the idea. So temperature is a measure of kinetic energy. Heat is an exchange of energy. But ready for this? How do we know that heat is being exchanged? What evidence do we have? A change in temperature. Right? Remember when we said earlier that we can't directly measure energy, but we can measure changes in energy? That's an example of that. That when we measure temperature, what we're actually going to do is measure temperature change. And as we measure temperature change, we can then determine if heat is going in or if heat's coming out. Because if heat's going in, the temperature goes up. And if heat's coming out, the temperature goes down. So temperature is evidence of heat, but it's not the same as heat. Right, and that's what we're going to do next. That's what we're going to do on Friday. Yeah, that's where we're headed. I know, right? Shoot. But that's where we're headed on Friday. So guys, will you trust me and not take notes? This is what you need to know about these things that are called thermochemical equations. Don't write this down, just watch. Guys, this is what is called a thermochemical equation. If I had just given you this, you'd have no problem with it because it's just a synthesis reaction, right? But now we add this. And this additional information tells us when this reaction happens, how much energy is involved, how much heat or enthalpy is transferred. Now guys, importantly, what does it mean that it's negative? Is energy going in or out? out. So will this feel hot or cold? Hot, because it's giving off energy. As we grab a hold of that, the reaction's losing energy, and so we would experience that heat, that enthalpy being released. But guys, as you begin to interact with these thermochemical equations, next time in class, which Maddie actually will be the answer to your question, we're going to talk about where do those numbers come from? Where do we get the values for these thermochemical equations, and what do they mean? And what this means is this: if you burn 2 moles of hydrogen in 1 mole of oxygen, you will get out about 480 kilojoules of energy. That was the energy that made that cute little pop when we did this in lab last year. Remember, we collected the hydrogen from the zinc hydrochloric acid reaction, and you lit it on fire. And when you did, it went boop. And that's the energy that you represented, right? That's the exothermic nature of this reaction as it gave off heat and, in this case, sound. Now, guys, as we're thinking about these thermochemical equations, there's some things you need to know. First of all, this is an extensive property. Don't write these down. This is an extensive property, which means the more you burn, the more energy is given away, right? So the more matter you have, the more energy is involved. So what if you were to burn 4 moles of hydrogen? How much energy are you going to get out? Twice that much. You double this, you double the energy. That makes sense. Then, guys, in addition to that, these things are just for the moles represented. Also, these things are reversible. So, guys, if we come along and if we switch this reaction around, and if we make it a decomposition reaction, guess what else changes? The sign of the energy. So if 480 kilojoules of energy is given off when hydrogen and oxygen makes this much water, if you take 2 moles of water and break it apart, you've got to add 483 kilojoules of energy. That makes sense, right? And then, guys, finally these changes are phase dependent. So if this became a gas rather than a liquid, or a liquid rather than a gas, the energy changes would be different as well. Does that make sense too? Okay. So, guys, that's where we're going to stop today. What we're going to do, and actually I'm sort of changing my mind here a little bit. Next time, what we're going to do is we're going to talk about where do these numbers come from. And I know that I said that Wednesday we're going to rewrite the tests, and then Friday we are going to just move on. I think I may change that. The reason is because Wednesday during third period, we are going to start doing one of these thermochemistry labs where we're actually going to measure these numbers. And in order for that lab to make sense, you're going to need to understand what's called calorimetry. So, guys, I think what we may do is Wednesday in that short day, we're going to go over calorimetry. It actually will fit quite nicely in that short day. So I think, guys, Wednesday we're going to do calorimetry, and then on Friday we're going to rewrite your tests so that we can use our lab time more efficiently. So anyway, all of that to say, there's your homework, and we are done for the day. So, guys, I'm going to stop this, which means the thing's going to go away.